of the course. So yesterday we began by quantizing the field, looking out what are the operators and the states that you can take out of the field after quantization. So we finished with the description of the state under different representations with different bases coming either from the number operator or the position operator or the operator associated to the complex amplitude of the field. But that's good for pure states. We need to go to the representation using the density operator to really give account of mixed states, to include statistical uncertainties and uncertainties of classical origins on the description. So today, I need you to stress and elongate a little bit. Will involve some calculations that will be left as a PDF for the people from the ICTP to distribute it for you. I hope the mail was sent. Otherwise, just draw the pen drive with the folks and they will send it for you right after lunch. Try to follow me to the calculations and grab a bit of the idea of what's being processed, what's the operation involved. Because now we will begin from the density operators and the description that we came out of the pure states described by a vector in your Hilbert space. And from there, from this vector description, we built a matrix involving basically this contribution here of this projection, describing a density operator that here for a pure state is pretty evident, but comes with an attribute that the expectance of an observable is given by the trace of the product of two matrices. So now we'll be dealing with matrices, so we have doubled the space. Instead of using a vector, we're using 2D combination, going from 1D space to a 2D space. And while we increase the dimensionality, we can include now statistical mixture on top of that. And all the calculations we made for vectors for a density matrix involving vector states or pure states can be applied as well as convex sums of these matrices, of these pure states. So here enter the classical statistics. And by classical, I mean that it's a sum of real valued numbers whose sum add up to 1. Okay, that's nice. We have the number representation, as we have seen. But number representation goes into a discrete spectra. What if we try to go for a representation involving states like a coherent state? That was a suggestion that was made by Glauber and Sudarshan using what they called a P representation. P as a probability combination of these states represented by a combination of pure states. We'll begin by discussing this one, that's the canonical, that was the first one applied to optical fields. But then you see that was not the only suggestion. That's just the more evident, but yet it has some limitations on its use. We see here 3 possibilities. The P representation, the Husimi Q representation, and the old Wigner representation. We followed them, ending up in a nice example of measuring it on an experiment. For the description of those representations, I strongly recommend you to read the book by Scully and Zubiri, Quantum Optics. Also, there's some discussions on Walls and Milburn, but I think that here has a good description, but you see that specifically for Wigner representation, there's another book that would be very helpful. Going into all the details, you may say dirty details, or you may say beautiful details, depending on how you deal with math. But let's begin by the P representation on the way that was described by Glauber and Sudarshan. So let's begin by this way, okay? We have a density operator. In the N, in the Fock state representation, is described by this. It's basically a combination involving projectors between a state M and a state N of the field. So we may look for a description involving the coherent state basis. What's the advantage here? We want to come out from the discrete representation in terms of number states into the more natural, and by natural I mean that we start from vacuum and then we make a displacement representation using the coherent state. So there's the immediate attempt, okay? Let's just substitute this operator, multiplying both sides by units. So if we make this multiplication here, involving this identity, what we get at the end will be basically the projection of P in alpha and beta to coherent states, and the combination of this projector beta on alpha integrated in these 2D states for beta, 2D states for alpha. So we have a 4-dimensional state, a function of alpha and beta, and a projector. That will be associated, that should represent the same state as the projector of N, state N into state M, with a given complex weight in front. So this representation basically is the equivalent from one to the other if you change the basis from this discrete to this continuous basis. Okay, doable, but there's a drawback here. We come out from a discrete 2D basis into a continuous 4D basis, a 4D space. So that's only made things more complex. In fact, we expect to have some redundancy here. The point is that this function is a map of the density operator matrix in this 4D space. So this mapping could, maybe it could be improved. Maybe you could get down on your dimensions into a sort of 2D mapping involving now a continuous, involving continuous variables, but yet something that you can represent on a plane. So the first proposal is, let's have a try. Let's use the same beta equals to alpha. So it will be a function P of alpha, or can say of alpha and alpha conjugate, or P of X and Y, where alpha will be basically a combination of these two real-valued observables. And let's see what happens when we make this proposal here? So now we're taking only diagonal terms involving here projection of alpha into alpha. That was a suggestion made by Glauber and Sudarshan. First thing that comes out from this representation, or this attempt of representation, are that it's pretty useful to calculate any observable if you put that into the normal ordering. So first, all the annihilation operators, and then all the creation operators. You can take any function of A and A dagger, and by the proper commutation relation, put it into this formalism, into this normal ordering. When you do that, and you look at the expectance value of it, you'll be basically calculating the trace here of rho times this operator. So it will be a combination of rho, A dagger, N, A, M. And now we can make the use of an interesting probability of this trace. Let's all of us, those that are not familiar with this fact that can basically revert the ordering, take the last operator and putting it first without changing the value, the demonstration is pretty simple. You can just take a look here that you can take this trace. That would be the projection of A and B into N on both sides. You can introduce here an identity that comes from the completeness of the bases. And when you do that, you have a pair of C numbers. Now you can invert, but in fact your summation here comes over N and M. But you can invert the C numbers here without any problem. Unlike it would be if you're doing with matrices or whatever. So under the summation, you can change the ordering here. These are just C numbers. And now, when you add up over N, you get the inverse ordering of A and B. So now you get trace of B and A. It's not that if you take three operators like A, B, and C, you're going to take the inverse of it. That's not the case. It's the fact that you can change it to trace of C, A, and B, and then to trace of B, C, and A. Are you familiar? Who's familiar with that? Raise your hands. Okay. So there are some people that are not familiar with that, but there's this nice property. You can take the last one, bring it to first, and you get the same result. So on, so forth. Okay? That will be very useful. We'll be using it along the way. But the fact is that here, when you apply this at this point, you can put all your, I missed the hat here again, you can put all your annihilation operators as the first term in your trace, and the creation operators as your last term. And now let's do the substitution. Let's take this definition of your base matrix and put it here. It becomes clear now that can make use of the fact that these terms, the eigenvalue of the annihilation operator, and then what we have here is a complex number, alpha, taken to the nth power. And here we have the application of this operator from the right side into the bra alpha. So we have alpha get alpha conjugate taken to the power n. What's nice here is that your operators now have disappeared, and you have now a summation involving only C numbers. So you can invert here integration and summation independently. And what we have at the end of the day is that the expectance value will be the integral of your function, where we replace your operators, A and A dagger, by C numbers, alpha and alpha star. And what you'll be playing with now, using here the identity, is that your expectance value will be basically the integration over the complex space of a weighting function times your function of alpha and alpha star. You see that you have changed from operators calculated involving trace in a matrix into something that involves a function weighting the expectance, weighting the value of the function that you want, calculating it on every point of space with this weighting factor, as if it were a density function or a probability function. It works much like we're doing just statistics of the outcomes. Okay? So it's pretty neat. I mean, you don't need to worry about ordering as far as you take any operator that you want, you put it into this formalism of normal ordering. You can just using the commutational relations and shuffle everything and put it in this right ordering, and then use this function as a probability. So it's nice. Now the point is how to calculate your function P, your Glauber reduction P function. If you can take that, you can use that as your density operator, just as the same as it would be for a density operator. It will be the mapping of your density operator into a function involving a complex values. So we can begin by this projection, the symmetric projection in beta and minus beta. So using this relation here of this projection that gives you this Gaussian, okay, with a complex term here, what you have applied here will be evolving into your function, a Gaussian, and here a Fourier transform in a 2D plane. So you can take the inverse of this 2D Fourier transform and see that you can evaluate this function from your density operator. If you project it on both sides on a position beta, and it's symmetric, having here a weighting factor, that's the exponential of this modulus of beta, and this 2D Fourier transform, 2D Fourier relation, this oscillating part here. You see here you have only an imaginary term on your exponent. Okay? Any doubts here? Questions? Too mathematical? You have to take the calculations, but take the message here. You'll be basically taking your projection of your density operator involving two symmetric positions in your phase space, relating these two symmetric positions. And what you have at the end will be a weighting factor that's involving an exponential. And here a term involving the oscillatory part, mapping a coupling beta and alpha. What you have at the end, when you integrate, will be alpha, with also an exponential here for alpha. It's a way for you to write P once you have rho. It's just the 2D mapping that you have. Let's take some simple case. I've mentioned the case of thermostates last class, but here let's see the highest entropy case of the mostly mixed state that you can have. That's just the thermal state. If you look at your density operator, it will be something that involves only the diagonal terms in your matrix, with a weighting factor like this involving the mean number of photons. And this mean number of photons comes from the Maxwell-Boltzmann distribution, will be something involving the energy of the photon divided by the temperature times the Boltzmann's constant. Okay, -1 is here, it's not on the exponential. Writing is not as nicely and clean. But the fact is that you have just something that looks like this exponential going down. So here we have the probability of finding 0 or 1 or 2 or 3, so on and so forth photons that are the diagonal terms of your matrix. Here for a mean number of photons equals to 5. Here for a mean number of photons equals to 10. So you see that always the leading probability is that you find no photon for a thermal state, then this decaying as you increase the number of photons that you're counting. What it happens when we map this into a Glauber-Sudarshan distribution, a representation. So taking this rule, what we have here will be an exponential leading to a Gaussian distribution. And when we apply it into the calculation here involving all this complex transform and this term, using this relation for the oscillatory part and the Gaussian envelope, what we have at the end of the day will be just a Gaussian distribution centered at the origin with a width that involves the mean number of photons. So you can see that your thermal state is directly mapped into a Gaussian centered at the origin. And the width of this Gaussian is basically given by the number of photons that you have, roughly speaking, on the temperature that you're working with. So this Gaussian distribution can give you a positive valued function that's basically the probability that you find your system in a given alpha state, mapped for any alpha in the complex plane. So that's really something that has the smell and taste of a probability distribution. That's fine? Okay. Let's see something different. Let's look what happens for a coherent state. And here is another way of taking the evaluation that's taking the trace. I didn't went to the dirty details of the proof. I leave that for you to read on the Scully and Zubari book. But you can take the trace of your rho times delta of alpha star minus A dagger, delta of alpha minus A. you have this delta function involving C numbers and operators. And using this definition of this delta function, you can take the trace of this that you'll be mapping you the P and the global subduction P function. Okay, once again, you can take the cyclic property, and when you take the delta function here applied on B, what you have is delta of alpha minus B, and same here, alpha minus beta. Same on the other side, alpha star minus beta star. So that's basically what you call delta square of alpha minus beta. So what you see is a 2D delta function. Okay, that's also reasonable, sort of. It's not something like a very smooth function, but yet, if you have a coherent state, it's pretty evident that what will be given is a divergent density of probability of finding your function at that given state. When you integrate that, you have the single value of 100% probability of finding your state there, at that position on your 2D plane, on the position beta. So it's extremely singular when you go to a coherent state. Fine with that? Let's take one step further. That's what I just said. So if you take your density operator here, when you make the integration using this delta function, it just returns you the operator, the density operator beta. Let's see a number state. And now things comes creepier. When you take this projection here, you have a function like this, that once you integrate, you have this term involving here something that grows up with a polynomial function. You can rewrite this as the derivative on nth order of your Fourier transform. And what you have here, this Fourier transform integrated over all the plane, is basically a delta function on 2D of alpha. And what you have is that your function here is not singular, is the nth and mth and an m here derivative of a singular function. So I can say that's pretty awful. You're not going to draw that in a 2D plane. I mean, can be a tool for calculation, but it's not something that you're going to measure and map and describe it as a function. And here come some aspects of this function. So it's not really a probability function, so we call it a quasi-probability function. It has some properties of a probability function, but yet has some peculiarities, and you need to use that with care. Question on first row. Let's see where's the microphone. There's one first question. Okay.
Thank you. The fact that thermal state is normal in the pair representation, I mean, it's normal in the coherent state basis, but also is diagonal in the number representation. What it means, because in coherent state are more close to the semi-classical states, but number basis of focus states are more not classical ones. So we have like a normal representation of the thermal state in both bases. It's like a...
That's a nice point. Remember that I mentioned that the coherent state is a sort of the most classical state, the things that comes closer to the classical harmonic oscillator, where take a pendulum, displace it, and let it swing, okay? Or a coil and mass then you take out of the rest position, and then it oscillates. That's the coherent state if you go quantum mechanically. So that's really the classical quantum frontier. A thermal state is just the average of a whole set of different harmonic oscillators, and then you look at them randomly. So they have a complete fluctuation in phase and amplitude. So you have a random distribution on your outcomes. What you have is a certain, going quantically, you see a certain number. So what you say, if you go to the mapping of the Kalb-Sudarshan function, there'll be a Gaussian distribution. So basically you have a process, you have a random kick that takes this process out of initial state without shifting. Eventually, you can switch energy between points or you can change the phases. But this process, this inhomogeneous process, will give you a Gaussian distribution due to its inhomogeneity. And now I got a twist if it's homogeneous or inhomogeneous. It's just trying to remember here, comparing it with the situation of atomic lines, for instance. The Gaussian distribution that you have from the atoms. So you have this random distribution that leads you to a Gaussian profile. So they have this Doppler broadening of atomic vapor, for instance, of your laser line due to this random process. So that will give you the broadening of your line. So that's basically the same idea that you have here. You have a set of harmonic oscillators, and each one of them is suffering a random initial condition, and that will lead you to this distribution of your possible states or possible outcomes if you take a measurement on this random sample. That's classical. Okay, you have a distribution of probabilities over a certain sample. Or you can have two different states that you can take randomly, so it will be a combination of random alpha and a random beta. But here, this is a state that has no classical source. It's the eigenstate of the Hamiltonian when you go into the quantum regime, into the quantum representation of your problem. So it has no corresponding classical source. And now that leads you to those extra singular functions. So that trace a clear boundary between the classical and the quantum state of light.
Sorry, can you please repeat the motivation behind the quasi-probabilities functions?
The motivation for looking for a quasi-probability, or why it's quasi-probability?
For looking.
For looking. The fact that if you go to that P number, to the density representation in terms of number states, it's quite easy for you, let's say, pushing quite hard here, saying that it's easy for you to take the diagonal of your light field. Consider that you have a detector that can resolve numbers, number of arriving photons. So you take a first measurement and you get this, and then you get this, and then you take your diagonal statistics. Now, to map that and get the off-diagonal terms, you need to begin to apply some displacements over your state. And looking at those displaced states and seeing the off-diagonal terms. They're going to appear, for instance, when you look at something like the coherent state. You see that the coherent state, you have many off-diagonal terms. So taking our matrix here, if you look at the diagonal, you have a strong density here. So I'm going to the limit. Here's a discrete space, N and M. So taking it so small that you see it as continuous. So the coherent state, you have a density here along this line. that will go as a Poissonian distribution, but also you have terms appearing here on the off-diagonal. Those off-diagonal terms will be basically, if you take a look into n, alpha, alpha, m. You can just sit and evaluate and see that's non-zero. So those off-diagonal terms are important to define that as a coherent state and not just a mixture of a number eigenstates. To make that is subtle and make the measurement, and then you have a combination of these off-diagonal terms. So it's quite tricky to see that. In fact, resolving numbers of photons is something that's coming available only now, that you can really buy photodetectors that give a fair number of photon counting, going to up something like 10 or 20, depending on how much money you put on that, and it can be a huge bunch of money. While a photodetector will cost a single photodetector, as we're going to see tomorrow, that costs you some few dollars. But the difference that is not going to be working on this small photon number, but with high intensities. And then you can use interferometry to measure your state in the continuous variable domain. So basically, it's a way of doing your physics, but there are some facilities that comes from the fact that, okay, first, this state is not a natural state. It's not something that you produce from scratch on your tabletop. So working with coherent states is a more evident way to start with, and is a more evident way to measure your state. Yet, okay, this P function is not very convincing as a useful tool, because they're not going to measure that. I mean, okay, thermal state is pretty easy. You get that Gaussian distribution, but that's pretty evident. Whenever you have a thermal random process, what you get in the output is a Gaussian, being the random walk, dispersion of molecules in a gas, and or Doppler broadening of light emitted by crystals, so on and so forth. So the motivation for it is to map that as a 2D function that you can treat as a probability, and making life easier to describe the state. It's not, remember, this P is not the density operator, but it's a map of the density operator. And from that, you can calculate the density operator. So it's equivalent. You don't need to really calculate the density operator, but you can use just this quasi-probability function. Other questions? So, given the beauty of the number states, we have a good reason for looking for other solutions. In fact, if you look way back in the past, independently, Sudarshan go to another possibility of playing with this representation, but now mapping it in the other way around, something that was proposed by Husimi quite a time ago, in fact, in the 40s, in a Japanese journal. So you can see that's quite easy to go, not so popular at that time. Communications were quite rough. It was before Pearl Harbor, but yet things got noisy after that. But this Husimi distribution comes with some advantages. I'll begin by my claim by using a different ordering of the operators. So the Glauber-Sudarshan used the normal ordering for evaluation. So we'll be using Husimi to work with the anti-normal ordering Okay, once again, can go to Scully and to Scully and Zubairi. You see that while P function can be mapped using this normal ordering of delta functions, Husseini function is mapped by using the anti-normal ordering of your delta functions. First annihilation, and then first creation, and then annihilation. So when you use this mapping here, once again, it's just a way to translate rho into a function, a map. When you use that and you insert some term here and go through your calculation, using this delta function, you can basically see that you have the trace of rho times the projector alpha into alpha. Once again, you can reshuffle it, and at the end of the day, it translates simply over the projection of rho into the state alpha. So you see that the calculation here is quite simple, it's quite direct, and has a consequence. Okay, once again, it's normalized function. There's something very interesting, because if you're taking this projection here, you have only the diagonal terms of your state in the coherent state representation. So if there are diagonal states on a representation, then it's necessarily positive or necessarily non-negative, can be zero, okay. So works and tastes as a distribution. And once again, given the definition of your term here, so you can take any state as a combination of vectors with a weighting factor. So this is just the idea behind the density operator. You apply that, you check at the end that this term is bounded by 1. This term is also bounded by 1, so the Q function is limited, has no divergences. So it's limited to 1 over pi. So it's, as far as we can see, there's no proof that it's smooth, but has no divergences. It's integrates up to 1. It's positive, so it's pretty nice. Let's see if it's useful to evaluate any operator that we want. So you can take any operator O of alpha and of A and A dagger, put it in the anti-normal ordering, this weighting factor D and of D and M. And when you take that and make the calculation, let's play around with the ordering, and now we have this creation operator acting on the left on alpha, acting on the right of bra alpha, and the annihilation operator acting on the left of the cat alpha. When you do that, you can see that you have just the conversion of your operators into C numbers, and now the expectance value of your operator will be given by this, the weighting by the average of your operator evaluated at position alpha. When you use the anti-normal ordering to substitute your operators by C numbers, having Q as your weighting factor. Now it comes an advantage because it's pretty smooth, it's easy to calculate, and it looks like a probability function. Let's not call it probability, okay? It's a way of calculating it, evaluating an operator in the anti-normal ordering. Let's see some examples of it. First, okay, here is just the comparison on the sources. But most important, let's see what comes out for some states. Say, a coherent state. The Q function for a coherent state will be a Gaussian distribution. It's pretty immediate to calculate and see the comparison here. You have this Gaussian distribution compared to the delta function for the Glauber subduction P. Thermal state, if you go through the calculations, what you get at the end is once again a Gaussian distribution, but now with a width centered at the origin, with width that while for P, the width was given by the average number of photons. So if you have no photons at all, you get a delta function here, the vacuum state. If you have no photons at all, you have basically a Gaussian with a given width of order of 1. So you have a smoothing. You can see the Q function, a sort of a smoothing of your P function. And now let's see the number state. And what you get again is a soft function. Okay, you have here a polynomial term, but weighted by a Gaussian. So no diversions at all. And the position of the peak shifts for increasing numbers of photons. So the position here will be increasing given the growing number of photons here. And it will be symmetric with regard to the origin of your complex plane. So it's nice. It's easy to calculate. It's pretty immediate. But it's not so popular because at the end you have some problems in distinguishing if the state generated is of quantum origin or just a mixture of coherent states. If it's a simple mixture or has a quantum source. But it's a good tool for calculation. Okay? Let's go another step further and compare these two and the gains and problems of each one. P is too singular. It's good for classical states, but scrappy for non-classical states. I've shown you the Fock, but squeeze states can be as bad as these Fock states involving derivatives of delta functions. IFUSP is positive. Looks like a probability distribution, but everything will look like a statistical mixture. You don't see a clear frontier. So while P gives you a clear frontier that's hard to cross, in Q you don't see the frontier, and you don't know that you have crossed it through it. So there's no trick, even older than the IFUSP, for an intermediate representation. So here I'll be championing for the Wigner function from 32. It's sort of very popular one because you can see here extensive and very nice description in this book by Wolfgang Schleich. I strongly recommend because it plays with it, with the origins, and I'll give here just a brief overview on the topic. It comes from 32 on the quantum correction for thermodynamic equilibrium. And you can see here that's mapped on position and momentum as it was in the original paper by its projection, taking symmetric positions along the x-plane, and a Fourier transform on the p-plane. Remember that we made some calculation that led to a representation of your Glauber subduction P function as this projection involving the 2D complex plane of your density operator and a 2D Fourier transform. Here, there are good reasons that can go to the Wolfgang Schleich book that can make that with half the work just make the projections on the x-plane and Fourier transform on the conjugate plane. So using this 2D representation here, here is changing a little bit the terms just for the sake of following here the notation given by Slack book. So they have the 1D Fourier transform involving two positions. So you have the coupling of the state x2 prime into the x prime by your density operator. This function has this weighting factor to be normalized to 1. So we have a projector of your state here, making the quantum jump from this state into this state. So it would be the strength of a coupling. And when you make this 1D Fourier transform, you see that looks remember pretty much on what we had here, the Fourier transform, the projection, but we are missing this exponential, and that makes a strong difference. So this equivalent to a dipole moment in a given transition can sound as arbitrary. You can go through the paper to see some reasoning for that, but the important point, it maps nicely your state. Let's start with the marginals. So what are the marginals here? You have a 2D representation of your state. You just have a random way of mapping your state. This random way of mapping is not supposed to work as a real probability function, density of probability function. But if you take this function and integrate along the momentum, so you have this 2D function, and you integrate in the transverse direction, you get a function in x, and through this integration, you have basically the expectance value of rho projected into eigenstates of position x. We called it Q for the formalism on the last class. And that's just the probability distribution of getting an eigenstate x upon a measurement. That's what we call a marginal distribution. You take the average in one dimension to get the expectance in the other conjugate dimension. And now this is really a probability distribution, positive, limited, integrates to 1, and that's really the probability of getting x when you make a measurement over your problem. Okay? But come on, this function doesn't look so symmetric. Let's see what happens if you go to the other way around. Here, just to remember what we have seen in the class yesterday. So the probability of having Q in a given state will be given by this projection here. For those Hermite polynomials, leading to those square of Hermite polynomials. Let's see now in P, okay? If you now make the integration in X, what you get here is the projection between these two positions. So you have here the Fourier transform. And now going to the probability distribution in P, when you evaluate probability, calculate of getting P on this problem, you can see that you get basically the same thing as you have here. As a result, at the end of the day, you see that the probability of getting P is given by the integration in X of your Wigner function. So this marginal distribution works in both conjugate ways, in X and P. So it's a useful way to get the probability of getting an eigenstate, either in momentum or in position space. Fine with that? Questions? If not, let's see some properties, some interesting properties, like the overlap of quantum states. Say that you have a process, you have an initial state, gets you a final state, and want to see if at the end of the process, how far are these two states? You can take the overlap integral. Just something like that. Taking the trace over the product of these two states will be equivalent to take the integration of this pair of Wigner functions. Can make the calculations, but that's the idea. Whoops. Okay. This point, that will get the idea. And now, as a consequence, you see that this function is bounded. If you take the trace of rho square, that's basically a measurement of the purity of your state. When you make this calculation, it will be the integration of this Wigner function squared. So no matter if it's positive or negative, okay, now it's a squared function. In the integral of Wigner function is equal to 1. If you take this integration, it will be smaller than 1. So that's give you an idea of the area that you have for your Wigner function. That will be greater than 2 pi h bar. So the broader is the area of your Wigner function given by this integration. The less pure is your state. So it also comes with a measurement of the purity of how close it is to a possible eigenstate of a given operator. Also from the Cauchy-Schwarz inequality, you can see that the absolute value will be small, it will be bounded, so it has no divergences. Moreover, if you see that you can have two states that doesn't overlap, that means that the integral of two Wigner functions is not, while these two functions are non-zero, they are necessarily non-zero over all the plane, their products should go down to 0. So they cannot be just positive functions. They may have negative parts in order to have a cancellation of two states that are absolutely orthogonal. So there are negative values for the Wigner function. At the end of the day, what we know is that the Wigner function is bounded, quite smooth, but yet it can have negative values. And the nice part, that's not a problem, because the probability is not given by the Wigner function, but by the integration in the transverse direction in your Fresnel plane to the dimension that we are looking at, to the measurement that we are taking. And now I introduce the term Fresnel plane, because the Wigner function maps nicely into the Fresnel plane that I discussed in the last class. A subtle drawback here is that the observables should be in the symmetric order. So what we see here is that you can take your number operator, that's the normal ordering. You can use that when you're going to make a calculation using the P, global subduction P, or the anti-normal ordering. You can also use that. You're going to take your calculations. But when you're going to make calculations using the Wigner function as your weighting factor, you need to have that in the symmetric order. There's be a combination of symmetric and of normal and anti-normal ordering. So it'll be something like this. So these are the Hamiltonians of the free field. Here in the normal, anti-normal, and symmetric ordering. That's equivalent of saying this as the sum of x squared plus y squared. It's really nice when you have your operators up to second order. Above that, it can be quite tricky to define what's symmetric. Say, when you have something like a to the fourth, a dagger to the fourth. Symmetrization would mean to transform it into an expression involving a to the fourth, a dagger to the fourth, a dagger to the fourth, a to the fourth. If you can combine these two, it's symmetric. But also, you can have combinations like a to the 3, a dagger, a, dagger to the 3, a dagger. Combinating these two is also symmetric. And all the possible combinations that you can have here. Defining the weighting of each one of those terms can be tricky. Whoops. Thank you. Something was missing. So how many terms are you going to use? What's the weight of this combination? It can be quite tricky. The nice part is that it's pretty seldom that you're going to get orders beyond 2 in your evaluations. So most of the time, we'll be working with bilinear functions of a and a dagger. So if you look at the Wigner function for a coherent state, what you have here in your calculation will be a Gaussian centered at a given position in your phase plane. So it looks pretty much to what we had with a Husimi Q distribution, but a bit narrower. And now it's nice. I squeeze the state. You can see here that you have a different width of your Gaussian distribution in the dimension that you are squeezing, and the other dimension that will be anti-squeezed. Is be broadened. And yeah, maybe just a moment for recording purpose. Okay. Right.
Yeah, thank you. It was just to please ask you to repeat this part of the Wigner function in relation to the squeezed state.
To this, here for, sorry.
Just to repeat, please, the last part.
So this part here, if you make the calculation for the coherent state, you make that mapping using the definition of the Wigner function way back. A bit more. Yeah. Okay. So if you put here your coherent state, what you get in your calculation will be a Gaussian function like this. So the width of the Gaussian will be 1, given exactly the fluctuation that you have for the vacuum. But displace it, the center of your distribution to this position, x naught, y naught. So that will be the center of your distribution at a given position in a complex plane. Okay? And then, when you have a squeezed state, like the one that we calculated before, what you have now is a function like this. So the width here will be 1 over e to the 2R, so that be broadened distribution in the X direction, and squeezed on the Y direction. But yet, the center will be at the same position. That will be equivalent to that operation of squeezing and displacing the state. And what you see will be, once again, a Gaussian distribution. But since one of the quadratures of it is smaller, narrower than the one of a coherent state, we can say that's a state of non-classical origin, a state coming from a quantum source. And now, while you don't have that dramatic boundary that you have for the p-valued functions, that so basically is a function that you cannot draw, here you can draw, and in fact that is not given by, if you see that's, basically if you see that's not, you cannot describe it by analytical p function, it's non-classical. And then you can go to the Wigner function, you see what kind of non-classicality it has. Can be something like that, a squeezed state. So if one of the variances is smaller than that of vacuum, it is non-classical. But there are some other nice non-classical features, like for the number state. If you come here and look at it, the Wigner description will be a Laguerre polynomial with a Gaussian weighting function with a number of zeros that will depend on the excitation number of photons that you have in your field. So this will be, okay, the number state for n equal to 0, vacuum, just a Gaussian distribution. But then for the first excited state, you have something that has a negative Wigner function. And that's nice. That's a nice signature of non-classicality. There are strong discussions coming out on the necessity of having negative valued Wigner functions as a tool for quantum computation. Main points that you they should not be. There are some limitations to make calculations using only positive valued Wigner functions, or something that can represent as, that looks really like a probability distribution. But here you can see clearly the signature for first for the ground state, okay, that's classical, but this is quantum, and you have a negative. Here you have a negative function as well, with a positive center, and all these functions symmetric for a rotation around the position x and y equal to 0. In fact, before going any further on the Wigner function, just for a last term of comparison, any questions here? Just to say now that there are some situations where you're going to see your state described by this characteristic function. Once again, it is a mapping. You're mapping your row state into a function x. So you can say that your function, your quasi-probability distribution, will be the Fourier transform of your characteristic function. It's a nice way of seeing the problem in a quite, in a way that you put all the three representations into the same ground. And the way that you have is basically a way of writing your density operator in terms of a function involving here a C number n. So it can be calculated by the trace of rho times the exponential of eta times a dagger and eta star times a. Here, left in the normal ordering. When you do that in this normal ordering calculation, what you have is the P representation when you make the Fourier transform of x of n. Okay? It's another way of calculating. What's nice here is that if you go now for the anti-symmetric ordering here, you invert these two compared to what we had before. Now you get the semi-Q distribution. And playing with this nice and lovely Baker-Hausdorff relation, you can write here as using the normal ordering. And it's curious here, what you have is your displacement operator acting on your density function to give you the symmetric ordered characteristic function. And now, when you make the integration, make the Fourier transform, you get the Wegener function.
Excuse me? Can I ask?
Sure.
This key function, it is like a different way to describe our density matrix.
Yes, it is.
Okay, so we describe it in this way that can be anti-normal or normal, and so we can get or Q or P. Is this?
Yeah, it's nice that it's a nice point because in terms of mapping, it's pretty equivalent to those representations of the field. But the point is that you have a function that describes, but you're not going to apply that directly to any evaluation. In order to use that, to get it to a useful way, often you're going to map it again, this function again, through a Fourier transform into a quasi-probability function. Summarizing it, okay. You're going to evaluate these functions using distinct combinations. Here, I use the Baker-Hausdorff relation. So basically, you're using your displacement operator acting on your density, your displacement operator acting on your density operator, and evaluating the diagonal terms to get the diagonal terms in the coherent basis to get your characteristic function. Their difference now is that you have a weighting of a Gaussian to get the anti-normal, and here you multiply by the inverse of a Gaussian to get your normal characteristic function. In order to make an evaluation of an operator, you need to take these functions and make again a Fourier transform, and what you get will be the Wegener. Through the Fourier transform, this one will give you the Wegener function, the semi-Q, and the Glauber and Sudarshan P. Okay? And these representation functions can be used either to evaluate operators or to check out the classicality of a function. Fine? It's more a procedure than anything else. What's come nicely here is that you can now see the relation between P, W, and Q. You're going to see that the Wegener function from here is basically the convolution of your P function with a Gaussian. And you make this convolution, what you get is a function that's bounded and continuous, differently from what we had of those extremely singular functions for the P representation. Now, if you take the convolution by another, once again by a Gaussian, with the same width here, you can see, or you take a convolution of P by a Gaussian with the double or the square, the double of the area of the first one, or the Wegener by the same Gaussian with the same area. What you get here is this semi-Q that now it's positive, bounded, and continuous. So eliminate the negativity of your Wigner function. What's nice that zeros, there's a nice, should send you the reference by Matthias Vouchers. I hope I'm not misspelling his name. On PRX, a review on Gaussians, on non-Gaussian states, where it demonstrates that zeros in the Q function implies in the negativity of the Wigner functions. So the negative value of the Wigner function will be telling you, or the zero in the Q function will be telling you that you have a negative value on the Wigner function. And that's an important resource for quantum computation, for quantum tests. There are things that you need, those negative Wigner functions, that you cannot play with only squeezed states. Like different criterions for entanglement. Say violations on Bell tests will demand those negative values. While entanglement, just entanglement, they do not demand negative values on your Wigner functions. Okay? Okay, made this for only one mode, but you can have here those functions evaluated for any set of modes. 2 distinct modes, 3, so on and so forth. Okay, you're not going to draw those functions. They'll be hard to draw, but they're immediate for the use in calculations. So the Wigner final claim for the Wigner functions that you have a quantum classical frontier. This is your coherent state. I'm looking at just a Gaussian, cutting at the half of maximum, and then you have this circle for a coherent state, and the squeezed state, you compress the top of it. Or you can have negative values states. Fox state for n equals to 0 is the same Gaussian distribution. Or you can have something with those ripples coming out from the center. Like here for n equal to 3, you have 1, 2, 3 zeros of your Wigner function. So you have this undulation here. What's nice is that those are drawings. Now I'll show you some measurements. I strongly recommend you look at this paper from the group of Serge Roche. You've heard about him earlier this day. So basically took that nice tool that he has, 2 superconducting mirrors that make a high quality cavity that can manipulate 2 ways. It can irradiate light into it, okay? Electromagnetic waves would be more appropriate since we are in microwave regime. Or it can use atoms to go, either this source can put light or put energy into it using a classical source, producing coherent states, or it can send atoms here, specially prepared to interact with the cavity and lead one photon, then another atom to put a second photon, so on and so forth, building up photons into it. Can make also measurements with those atoms, depending on the tuning that he has, and make the use of those atoms as the probe to measure the state of the cavity. So combining both the driving field here, the horn, and the atoms, it can manipulate or measure the state inside this cavity. For instance, it can get something like a coherent state. So this is a mapping of a coherent state, and when he goes to the density here, you can see a peak on the diagonal terms. There'll be up to 1, 2, 3 here. So be the average state with the average of number of photons of equals to 3. So it'll be something like alpha with alpha around 3, and can map that either on the number representation or evaluate the Wigner function out of it. You can see here all the off-diagonal terms that are characteristic of the fact that you have a coherent state, not really a mixture of different probability densities of number states, but really a smooth profile. Or can tweak a little bit and produce Fock states. Okay, here the evident one, 0 photons inside the cavity. When you make the measurement, see that there's some residuals here in state, making the tomography. That's the kind of Wigner function that it has. Okay, there's some wiggles around, but still pretty centered, all positive, mostly. There's some effects here on the borders. Now, when you put a single photon inside the cavity, what you see is a negative valued Wigner function. 2 photons inside the cavity, that's the Wigner function that it has, with a negative ring showing up here, blue for negative valued. And then 3 and 4 photons, so on and so forth. You see that fidelity here is not so fantastic. You have some vacuum yet. You begin to lose your fidelity to a pure state. You begin to have a mixture, and that affects the resulting Wigner function, but yet a pretty nice reconstruction. Or, one step further, you can raise kittens inside that and let them die. Schrödinger kittens, like this, even or odd kittens, of being simultaneously with an alpha and a minus alpha state inside the cavity. Not a probabilistic distribution. That would be just 2 peaks here and here. But since you have this combination, what you have are those fringes in between when you go to your Wigner function. And that's the signature that you have a quantum feature, especially those negative values here. So this is a combination of those states with a peak here on the positive, or here and on the other way around, depending if you're making a symmetric or anti-symmetric combination. So those Wigner functions are something that you can really measure and map it from the cavity, or from your detection process with the help of displacement operators. So that's nice. You can see that you can reconstruct your state, you can get information of your state using those quasi-probability representations. It's not all things that in quantum optics that you'll be dealing with that. It's just a convenient way to play with your system when it's not in a pure state and get this nice mapping in terms of a function that you can measure and reconstruct. And some characteristics of those functions will tell you if your state is useful for something. Either quantum communications, either information processing, either quantum measurements, measurements that you count on quantum features to improve the outcome. Okay? That's all for today. Thank you for your attention. Questions? Is everybody too hungry for that?
Thanks for the lecture. In the experiment we were watching, the Wigner function is obtained directly from the experiment, or it is reconstructed from the number representation?
There's a nice way. That's basically the evaluation. We have to go through the calculation to get the exactly. I may be mistaken by the description, but evaluates the parity of a measurement of a given value at the probability of finding 0 photons when you make a displacement of your state. Displacement is very easy. You just apply that horn and turn it for some time and displace your state. And you make a symmetric displacement and check the parity, and then you can around a given position, then you can map the Wigner function at a given position from the parity, the evaluation of the parity operator. The details were something that came out from discussions with Luis Davidovich. So it was a long-term collaboration that Nissim Zaguri and Luis Davidovich have with the group of Michel Brun, Jean-Michel Raymond, and Serge Roche. And they made all those, and that come all the ideas of using those cavities to build up those exotic quantum states. So we can really measure this Wigner function point by point and make the reconstruction.
Okay,
There are other ways of doing that. Unfortunately, I think that I have hidden the transparency here. Damn it. Yeah. But other ways of getting the Wigner functions are by making the tomography of a state. You project this thing, taking an orientation of measuring one quadrature. So you measure this quadrature and see the shadow of this quasi-probability distribution, and you get a real probability distribution. Then you turn.
You do that with homodyne detection, right?
Exactly.
Okay.
So you measure quadratures. And then what you get are those shadows, those marginals, these marginal distributions. And from the marginal distributions, you can make a calculation, an inverse inverse radon transformation. Not random, radon transformation. And get the structure inside. Okay, that depends much on the precision of your measurement, on the quality of your data, and on the binding to get a proper reconstruction of state. When you have a traveling wave, often is what you do. You make that transformation, and you make, okay, homodyne is the easiest way of measuring something. And then you take the mapping out of your homodyne measurements. Or in the group of Serge Roche, it's inside the cavity, so it takes the atoms and the horn to make the evaluations.
Thank you.
Okay, thank you.
This